Well, hello and welcome to the 29th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in the middle of understanding the identification problem from a given data set, which is a trajectory, and we have gone up to this idea that it is important to construct the kth Hankel matrix from the trajectory data, okay, which has k plus 1 times q number of rows and infinitely many columns. And it turns out that all the annihilating annihilating polynomials of the trajectory whose degrees are less than or equal to q, should not write w here, are in fact given by vectors in the left kernel of this Hankel matrix. So, then in order to find out this, so identification of a system tantamounts to finding out this annihilating module, which we are trying to find out by parts, because I need to find out n0, n1, n2 and so on, and these guys I can find out by computing this left kernel of various Hankel matrices. At first sight it appears to be outrageous, preposterous even, to find out this nk for all possible k, but then as we discussed in the last two lectures, that I do not have to do it, I do not have to find out this nk for all possible k's, because I can stop at some point of time, namely after the saturation point, because at some point beyond which the ranks of these Hankel matrices will only keep increasing at a fixed rate. Once the rank increase at a fixed rate, it turns out that I do not get any new kth order equations, k plus first order equations, if all k plus first order equations can be obtained by shifting the kth order equations. Likewise, k plus second order equations will be found out from k plus first, which in turn are obtained from n from k. So, k plus 2 order equations are obtained from k and less, k plus 3 also ordered from k, k plus 4 also from k, and so on. So, everything will come from nk itself, provided I have gone up to the saturation point. Let us try and understand these phenomena a little more clearly by looking at a few toy examples. So, first one I will look at a very simple example to just give you a glimpse of what we are saying in terms of these ranks and so on. Suppose the trajectory data w is given like this. It is say 0, 1, right, then 0, minus 1, 0, 1, 0, minus 1, like this. That is my trajectory level data. It is a scalar system. So, I expect one single equation for this, right. What is that equation is what I need to find out. Obviously, because it is scalar and these are non-zero numbers. So, I mean not all numbers are 0. So, of course, there are no 0th order equations, 0th degree annihilators are not there. So, if at all I should expect for first order annihilators. So, what to do now? H0 is just this w again. So, I can start from H1 itself. What is H1? It will have 2 rows and infinitely many columns. So, I start with 0, 1, 0, minus 1, 0, 1, 0, minus 1, dot dot dot. Then I have to shift it by 1. So, 1, 0, minus 1, 0, 1, 0, minus 1, 0, like that. That is my H1. What is the rank of H1? You can easily compute that this implies this implies, so I should write the rank on the right side. Okay. So, each time I write H, I will write its rank on the right side. This has, what is rank D 1? D 1, can you tell me? It is 2. You see, I already see one 2 by 2 invertible block here. So, therefore, these rows are certainly linearly independent, both of them are. So, therefore, rank is equal to 2. So, there are, if the rank is equal to 2, then there is no hope of finding any first order equations. First degree annihilators are not there, because there are nothing in the left kernel. Left kernel is equal to 0. What if I look at H 2 now? H 2 is once again 0 1 0 minus 1 0 1 0 minus 1, like that. That is the first. Then I have 1 0 minus 1 0 1 0 minus 1 0, like that. Then I have one more shifted version, that is 0 minus 1, 0 minus 1 0 again, plus 1 here, then 0 again, and a minus 1 here, and 0 again, and a plus 1 here, like that. Now, what is the rank here? I can immediately see something in the left kernel, namely, you see the first row and the third row, they are just minus 1 times of each other, they are multiples of each other. So, row 3 plus row 1 is equal to 0, correct. So, at least one relation is there, and rank is at least 2. So, therefore, rank here must be exactly equal to 2 again. Okay. What is the relation, however? The relation here is, if you want to find out the left kernel, why should I do it? Let me do it in the next page. Left kernel of H 2 is given by, remember 3 rows are there. So, it will be of size 3, and I said that the first row plus the third row is equal to 0. So, 1 0 1, span of this, that is the left kernel. Okay. We can also go ahead and compute H 3, which will come out to be 0 1 0 minus 1 0 1 0 minus 1 dot dot 1 0 minus 1 0 1 0 minus 1 0 dot dot dot, then 0 minus 1 0 1 0 minus 1 0 1 dot dot dot. This will be minus 1 0 1 0 minus 1 0 1 0 dot dot dot, like that. And you can see that now there will be what is the rank here? I have, of course, I have that earlier one, right. So, these 3 rows are linearly dependent. In fact, this row plus this row is equal to 0. I can now notice that this row plus this row also is equal to 0, that is the second and the fourth row are also equal to 0. Yeah. So, if I write down those left kernels, left kernel of now H 3, right, that is what it was, H 3. Notice carefully, that is given by 1 0 1, I have to put an extra 0 because now the size is increased. Okay. There are 4 rows now. This is just like left kernel of H 2, this is the embedding of left kernel of H 2 in the left kernel of H 3, this part. But apart from this, I also know that the second row and the fourth row, their sum is also equal to 0. So, that is it, this is the one, correct, and that is it. These two are linearly independent. So, 2. So, the dimension of left kernel of H 3 is equal to 2. Therefore, this will also turn out to be equal to 2. Yeah. and in fact you can just go ahead and do these calculations again and again and again, and you will see that the rank does not go beyond 2 at all, the rank will saturate at 2. So, that is the saturation point. So, this implies rho 1 is equal to 1, because it is d 1 minus d 0 and d 1 is 2, d 0 is 1. So, therefore, rho 1 is equal to 1, rho 2 is equal to d 2 minus d 1, which is equal to 0, correct. Then rho 3 is equal to 0 again, because it is d 3 minus d 2. So, once again it is 0. So, rho actually saturates to 0 beyond this point 1. Beyond this point 1, or should I say 2, what is the terminology? It is a matter of convention, beyond which yeah, right. So, capital K is equal to 2 now, yeah, capital K is equal to 2 now. Yes, capital K is equal to 2 now, because capital K is equal to 2 for any small k which is 2 or more, I should get rho k plus 1 is equal to rho k. So, that means starting from rho 2 onwards, rho 3 is equal to rho 2, rho 4 is equal to rho 3, and so on. So, my capital K is equal to 2 in this case. Okay. Now, if capital K is equal to 2, notice when capital K is equal to 2, beyond this guy, when I compute left kernel of H 3, I see that although I get a new equation, new independent equation, but this new independent equation, I mean I get an independent equation which is 4th order, but this is not a new 4th order equation. Why? Because it is actually a shifted version of the old equation. Let me write down the polynomial versions of this. What is the polynomial identification of this? This is R 0 is 1, R 1 is 0, R 2 is 1. So, this is actually xi plus 1, because this goes with 1, this goes with xi, sorry, this goes with xi squared, this is xi squared plus 1, this is xi squared plus 1. Once again here it is 1, this goes with xi, this goes with xi squared, this goes with xi cube, this goes with 1, xi, xi squared, xi cube, right. So, this equation once again corresponds to the same xi squared plus 1, but this one corresponds to what? This one corresponds to xi cube plus xi, but notice that this is nothing but xi times xi squared plus 1, which means this is not a new equation, new 3rd order equation, I was saying 4th order, sorry, this is not a new 3rd order equation, yeah, because it is actually obtained from this 2nd order equation and it is shifted version of that, or multiplied by xi version of that, you see. So, I am not getting any new 3rd order independent equations. Reason is because what is gamma 2? Gamma 2 is equal to rho 1 minus rho 2, right. Gamma 2 is equal to rho 1 minus rho 2. What is rho 1? 1. What is rho 2? 0. So, this is equal to 1. So, I was expecting one new 2nd order equation and I did get that. What is gamma 3? That is the new independent 3rd order equations, that is rho 2 minus rho 3. Now, what is rho 2? Rho 2 is 0. What is rho 3? Rho 3 is also 0. So, this is 0. So, I do not expect any new 3rd order equation, and that is what is happening here. So, I do not expect any new 3rd order equation. So, therefore, I can now stop and say that okay, I have found out what is N2. N2 in fact is the span of the R span of xi plus 1, xi squared plus 1, the span of this. Okay. And so, I claim that my most powerful unfalsified model is given by kernel of sigma squared plus 1. Yeah. We verify this a little later, that this is indeed the MPUM, but at least you understand how to get to this N2. Yeah, no new equations actually mean that if I want n3, then I just need to look at xi squared plus 1 and xi times xi squared plus 1 and the linear span of that. If I want n4, I just have to look at xi squared plus 1, xi into xi squared plus 1 and xi squared into xi squared plus 1, and that is it, linear span of that. Yeah, that will be n4 and so on. Yeah, or in other words, it turns out that if we want anything in n, then that can be actually that is actually the linear span of xi squared plus 1 times xi into xi squared plus 1 times xi squared into xi squared plus 1 dot 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 forever. That is the linear span, which is the same as looking at polynomial. So, if I look at a ordinary linear combination of these guys, which looks like this, plus dot 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 plus a n xi to the power n xi squared plus 1. That is the typical linear combination of an element in n from what we have gathered. Then this can in general be written as a0 plus a1 xi plus dot 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 up to a n xi to the power n. That is a typical polynomial in R xi multiplying xi squared plus 1, which then tells us that this n is nothing but the ideal generated by xi squared plus 1, the submodule generated by xi squared plus 1. So, therefore, my R xi is indeed equal to xi squared plus 1. So, I found out this n, yeah, the annihilating module, its kernel representation description, that means a kernel representation a matrix, a finite size matrix whose row span is equal to my annihilator, annihilating module. Once I have that description, I have actually found out a model for the system for the given data. This model, the fact that this model is also the MPUM is something that we will see in general. Yeah, after we have done these examples and we have understood these special sequences of rho and gamma and d non decreasing, rho non increasing, yeah, and gamma finally saturates to 0. Okay. Now, let us look at this other example. This was kind of very simple because it saturated after some time immediately. I did not get any sense of what we meant by new equations that are not obtained from the shifted version. So, for that I actually need a system with q equal to 2, that means 2 manifest variables. Did I write example 1 there? Then I should write example 2 here. Yes, I did. Example 2. Okay, W is given by 1. I am just concocting it, you will be able to see it immediately. 1 0, next is 1 1, next is 1 0, next is 1 minus 1, next is 1 0, sorry, next is 1 1 and so on. That is my trajectory level data. There is no need to write down the Hankel matrix of the 0th Hankel matrix, because you can easily see that they are linearly independent. Yeah. So, no need to write that. I start with H1. H1 here is, so like before I will do the same exercise. I will write H1 and then I will write its rank. H1 has how many rows? 4 rows. 1 0 1 1 1 0 1 minus 1 1 0 1 1 dot 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 dot. Okay. This will be 1 1 1 0 1 minus 1 1 0 1 1 1 0 dot 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 dot. 4 cross infinity size matrix. What is its rank? Do you see any relations already? Is can it rank, its rank be equal to 4? Is it full row rank? Obviously, it is not full row rank. It has at least some one thing in its left kernel. You see, the first row and the third row are exactly the same. Yeah. So, first row, third row exactly being same would imply that there is at least one vector, one non-zero vector in its left kernel. When there is one non-zero vector in the left kernel, then the rank can be at most 3, not 4. Is it equal to 3? Can you check whether this rank is equal to 3? Well, I can take the first row and the second row and the third row. If I take these 3 rows, I can verify that indeed, look at this. Yeah, I will use a different color. Let us say a purple color. I will look at this and this and this, which is this matrix 1 1 1 0 1 0 1 0 minus 1. This has determinant non-zero. I can expand the determinant with respect to this guy, which would mean I exclude this and find out the determinant of this, which is 1 times minus 1 minus 1 minus 1 times 1, which is another minus 1. So, equal to minus 2 and plus minus plus minus plus. So, the determinant is actually equal to minus 2. Because the determinant is equal to minus 2, this is a this is a non-singular block. I am removing this now. It is a non-singular block. Because it is a non-singular block, the rank will be at least 3, but it cannot be more than 3 because there is one dependency we know. So, therefore, rank here, oops, sorry, I should change the color. So, the rank here it is a different color. So, the rank D 1 is equal to 3 here, and I am supposed to write down the left kernel. Because the size is 4, rank is 3, left kernel dimension will turn out to be equal to 1, and it is the span of, see, first and third row are the same. So, 1 0, I can put a minus 1 here, minus 1 0 1 0, that is left kernel of H 1. Great. How about H 2? H 2 is going to be size 6, no. So, 1 1 1 1 1 1 0 1 0 minus 1 0 1 1 1 1 1 1 1 again, then 1 0 minus 1 0 1 0 again. Now, 2 more rows, once again 1 1 1 1 1, but now a shifted version of this guy, which is 0 minus 1 0 1 0, we have minus 1 here, dot 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 dot. A 6 cross infinity size matrix. Now, something interesting happens. What could be the rank? Rank is 3 or more, of course, because it contains H 1, but how much is the rank here? Okay. Now, I need to find out D 2. Now, I can do that by finding out left kernels, yeah, right, left kernel of H2. So, first I notice that this guy that I had will continue to be there, minus 1 0 1 0, but I need to add 2 more zeros here because now I have size 6. Why is that so? Because once again here same thing repeats, no, one first row and the third row are the same. So, I should notice that, but beyond that, so that is my first order equation, that is the only first order equation that I have. Are there any second order equations? To notice first, to get that, first notice that, okay, you see this first order equation that I had, a shifted version of that will still work, isn't it? So, what shifted version? You see here the sizes are 2. So, when the shift happens in blocks of 2. So, if there is a shift in 2 block shift, 0 0 will appear here, minus 1 0, that is the shift of this to this, and then there is this 1 0 which now should shift to 1 0. Now, let us see what does that mean. It means first, second, third, fourth, fifth. Third and fifth rows must be the same. Is that so? Let us see. This is the third row, fourth, fifth row, indeed. Now, let us see. Third and fifth row are also the same because it is just 1, correct. So, once again you see I have a second, this is a second order equation. Why? Because this guy multiplies to 1, this entire thing multiplies to xi. Here this guy multiplies to 1, this guy multiplies to xi, this guy multiplies to xi squared. This is of course a first order equation, this one is a first order equation. But what about this guy? This is 1 which is 0, this is coefficient of xi which is non-zero, this is coefficient of xi squared which is also non-zero. So, this is indeed a second order equation, but it is not a new second order equation because I have actually obtained this second order equation from my first order equation. What was that? From my first order equation, you see this was my first order equation, this is second order equation which is obtained from this guy, and it will become clear once I write down it as the polynomial matrix. What is this? This is xi times 1 0. So, xi 0 plus 1 times minus 1 0, which is xi plus 1 comma 0, that is the row vector. What is this row vector? This row vector is xi squared 0 plus minus xi 0 plus 0 0, which is nothing but xi squared minus xi and 0, but that is the same as xi times xi plus, I am sorry, I wrote plus 1 by mistake, should be minus 1, oops, yeah, once again wrong, xi times xi minus 1 0, lovely, no. So, this second order equation is not new, this is not new, this has been obtained by shifting an old first order equation, yeah, but they are linearly independent. As far as linear dependence is concerned, the two are linearly independent. So, actually in the left kernel I have 2 linearly independent equations. Can I have more? You see, now I notice something interesting. I notice a second order equation brewing in this guy. I look at the 6th row and I look at the second row. The second row and the 6th row are just minus 1 times of each other like before. What is that equation? So, let me get rid of all this. Okay, this is fine, I can keep it there, it should not matter, but I have a new equation now. What does it say? It says that the second row times the 6th row, they are the same. Yeah, how do you identify this with a polynomial? This goes with 1, this goes with xi, this goes with xi squared. So, this is then 0 xi squared plus 0 1, which is the same as 0 xi squared plus 1, great, no, this is this new equation. So, actually, and this obviously is linearly independent with this guy. So, in fact, I have 3 linearly independent vectors in the left kernel of H 2. What is the size? Size is 6. So, the dimension I know that is bigger than or equal to 3, yeah, but it cannot be more than 3, because if it is more than 3, then if it is more than 3, then the dimension of the left kernel will be less than 3, correct, but it is equal to 3, it is at least 3, we have seen 3 linearly independent vectors. So, therefore, D 2 must once again be equal to 3, which then tells me that rho 1 is equal to D 1 minus D 0, which is 1 here, because D 0 is 2, D 1 is 3. So, 1 is 1. Rho 2 is D 2 minus D 3, which is equal to 0. You can go ahead and calculate and show that D 3 will also turn out to be 3, rho 3 will turn out to be 0, that is the saturating point. So, once again the saturation point is k is equal to 2, sorry, k I said 2, but I wrote t, I do not know why. So, 2 is the saturation point. Because 2 is the saturation point, now I do not have to go beyond 2. So, therefore, now so what would be my equations then? This left kernel, yeah, this is the one that will give me the, what do you call it, this will give me the N2, and because this is the saturation point, I do not have to go beyond N2, and anything beyond N2 is actually a linear combination of things in N2. So, N2 as a vector is given by xi minus 1 0, comma xi times xi minus 1 0, comma 0 xi squared plus 1, the linear span of that. But then if I now want this n, I will notice that this is actually a multiple of this guy polynomially. So, therefore, polynomially I do not have to go beyond anything, I just look at the row span of xi minus 1 0 0 xi squared plus 1. Okay, that is the annihilating module for this example. Okay. You see how we get new equations. So, this gamma calculation will be interesting here. You see what is gamma 1? Gamma 1 is equal to rho 0 minus rho 1, rho 0 is equal to 2, rho 1 is equal to 1. So, this is 1. So, indeed I get a first order equation, one independent first order equation, that is what is expected. The left kernel here, this says that there is one independent first order equation. What is gamma 2 by the way? Gamma 2 is equal to rho 1 minus rho 2, but rho 1 is equal to 1 and rho 2 is equal to 1, rho 2 is equal to 0. So, gamma 2 is 1. So, that means I should get one more new first order second order equation, and indeed we got one new second order equation beyond these two, right. But what is gamma 3? Gamma 3 will come out to be rho 2 minus rho 3, which is equal to 0, because rho 2 and rho 3 both are 0. So, therefore, no new third order equations, because we have reached saturation. Yeah. So, I think with the help of these two examples you are able to at least get a grasp on what is happening as far as these invariants are concerned, right. But what is still remaining is the fact that this thing that I have been emphasizing so much, that go to saturation, find out left kernel and you are done. That gives us the annihilating module true, but why is this the MPUM? Yeah, that is something that we will understand in the next lecture. Okay, till then take care of yourselves, bye.